Yeah, good morning to all of you. In this lecture, we will simply analyze the classical mechanics of simple pendulum. Means how to study the expression of Lagrangian and various classical mechanical parameter corresponding to our physical system, that is known as simple pendulum. So if we have a simple pendulum, so before going to discuss the concept of Lagrangian, let me explain that what is simple pendulum in one word. Simple pendulum is a system in which a bob of mass m attached to a massless string of length L, which is shown in this figure, and this is again rest position. So simple pendulum. So simple pendulum is a system in which it is system in which a bob, this is known as bob of mass m attached to a massless string of length L. So this system is known as simple pendulum basically, and we will analyze the mechanics of this physical system via Lagrangian approach, which is analytical approach. So this is the rest position. Now if we displaced and if we disturb the equilibrium, what is our objective? This is in rest position or equilibrium position, no force. Equilibrium means all the resultant force acting on this system is zero, so that is known as equilibrium position. So initially it was in equilibrium position. If we disturb its equilibrium, it means slightly disturb this pendulum from their equilibrium position, from here to here. So there is an angle between this length is m, and this is reference point. This is reference point. I will tell you the exact meaning of this reference point later on. So this is known as, this is the displaced. If we displace slightly disturb the equilibrium by small oscillations, so that angle is known as theta. And what is this position? This position is, if this length is L, so this is L cos theta and this is L sin theta, and this is arc. Let's say this arc is S. So this point is C, this is O. So this point is C and this is O, and this is A and this is B. This is O, this is A and this is B. So this is the nomenclature of this system. So initially what is our objective? This is in rest position. If we will disturb the equilibrium position by applying some force, so if we will give some small oscillation in this direction, so this motion is in plane. So our pendula starts vibrating in plane, and we have to analyze the mechanics. Our classical mechanics means we have to find out the generalized coordinate, equation of constants, degree of freedom, and Lagrangian, and then Lagrangian equation of motion and its solution. So this is the overall objective in classical mechanics. So, and this is the corresponding to any physical system. This is not for simple pendulum. What is our objective in classical mechanics? To analyze the all mechanical parameter by Lagrangian classical approach. In this lecture by Lagrangian approach. So we have to set up a Lagrangian equation of motion, or we have to set up a Lagrangian then corresponding Lagrangian equation of motion, and degree of freedom, generalized coordinate, all the mechanical parameters. So in this case, what is our system? This is the system. Now this is in displaced position or disturbed position, and we have to analyze the trajectory of this disturbed system, not this. This is because this is rest position and this is displaced position. And what is our interest, whether it is in Newtonian, classical or quantum mechanics, is to study the mechanics or to study the various parameters corresponding to this displaced position instead of rest position, because in rest position or equilibrium position net resultant force acting on the system is zero. So in this, now the pendula is oscillates, and this is the nomenclature. Now what is the Lagrangian? What is the Lagrangian? Let's say this is. So before write the Lagrangian, L, which is again T minus V, which is 1 by 2 m qk dot square minus V qk. See, this is conservative system. In earlier lecture, I have discussed the concept of, I have already discussed the concept of spring mass system, which is also conservative system. This simple pendulum is also a conservative system. So in conservative system, potential is velocity independent. So velocity is only function of generalized coordinate. In earlier case, it is also velocity is simply half kx square, half qk square, means it depends only upon position. It is independent of velocity. So that system is known as conservative. Force derived from the potential. We have a restoring force. In earlier case, we have expression of restoring force. From that restoring force, we have obtained the expression of potential, which is integration minus f dot dx. So these are the conservative system, and the constraint corresponding to this system is known as holonomic constraints. I have already discussed the concept of in lecture 2 or 3. We have discussed the concept of holonomic and non-holonomic. So these constraints are holonomic constraints. I will tell you the meaning of holonomic in this lecture also. So this is the Lagrangian. What is our qk? So this is our kinetic energy, simply half m qk dot square, which is, and this pendula is all, see, this is physical system. So we can see the motion of this physical system is in plane. So whether it is in planar Cartesian coordinate, if it is xy, so we can consider the particle is now here, it is xy, or we can consider in r theta also. We can express our plane coordinate is xy or r theta. So this motion is in plane. So this motion is in 2D. So we have one additional constraints. So this is m qk dot square or half m v square or half m. What is v qk? We have two different kinds of qk, x and y. So corresponding velocity is x dot and y dot. So x dot square plus y dot square. This is the expression of kinetic energy. And what is potential energy? Potential energy is simply, if this distance is y, so minus mgy, minus mgy. So potential defines the system. Potential energy is energy due to its position. Potential energy is energy due to its position. So this distance is y. So now this distance is what is, in this case, what is our y? So if we evaluate the exact expression of potential, once we know the potential, then our life is very easy in classical mechanics, because we can, our kinetic energy is simply half mv square, and we can convert according to the equation of constraints. But if we have potential expression, if we are able to write the expression of potential energy, then we can easily write the Lagrangian, and we can easily predict all the mechanical parameter. So potential energy in this case is simply mg OC minus OB. So this is the potential energy, and this distance is BC. This is the general expression, minus mgy. But what is y? Mg BC, this distance. Because when our bob is at A, the potential energy is minus mg this distance. And there is a separate story about minus and plus. In some situation you will find potential is mg y, and in some situation you will find potential is minus mg y. If the system is, in this case, if the system we are looking, if this is the particle, if this distance is y, so potential in this case, this is the reference point. I will tell you the exact meaning, and this is reference, this point is, and particle of mass m is here. So in this case, if you are looking below the reference, if we are looking our system below the reference point, in that case our potential is minus mg if this distance is y. So in that case our potential is this. In this case, if we are looking, this is system, this is our reference point, we are observing our system above the reference point. In that case our potential is mgy. In this case, if we are observing our system below the reference point, here we are observing our system is below the reference point. In that case our potential is minus mgy. So this is simply the way to write or to recognize whether it is plus mg or mgy or whether it is or minus mgy. So it's all about the recognition or identification of potential, whether it is plus sign or minus sign. It depends upon this reference point. Now the potential in this case is simply mg BC. And what is BC? BC is simply OC minus OB. So minus mg, and in this case we are using minus sign because our reference system is this one. We are observing our system below the reference point. So mg, what is our BC? BC is simply OC minus OB. OC minus OB. So this is simply, let me revisit, OC minus BC. This is OC minus BC. This is OC minus BC. So mg OB. And what is OB? This distance is simply OC minus BC. Because initially it was in this rest position, it will disturb, so there is change in position of our system. So corresponding potential energy, when it is here, then we have different potential. If it is displaced now at A, our bob whose mass is m, its mass is m, this is particle whose mass is m. Now when it is at A, we have different potential. And what is that potential? Potential due to this. So the potential OB is mg, OB is simply OC minus BC. So this can be written as minus mg, and what is OC? OC is simply L, distance of length of the string L, and what is this BC? BC is simply L cos theta. BC is simply L cos theta and OC is L. So from geometry we can simply write as mgl 1 minus cos theta. This is our potential energy expression for this conservative system. Now what is our kinetic energy? So our Lagrangian is simply, let me erase this. So Lagrangian is T minus V, which is 1 by 2 mx dot square plus y dot square minus becomes plus mgl 1 minus cos theta. From this expression, what is our x dot? From this geometry, x is L cos theta and y is L sin theta. And what is x dot? L sin theta, theta dot. What is y dot? Differentiating with respect to t, L cos theta, theta dot. So x dot plus x dot square plus y dot square is simply L square theta dot square. L square theta dot square. So this is another equation. This is very important equation of constant. This is known as equation of constant and this is holonomic constants. So what is now putting the value of this system? So our Lagrangian is 1 by 2 ml square theta dot square plus mgl 1 minus cos theta. So this is the Lagrangian expression corresponding to this simple pendulum. Now check whether this Lagrangian is right or wrong. So how to check? Again we have very good statement, that is number of generalized coordinate is equal to, now if number of generalized coordinate is equal to number of degree of freedom, then it is correct, then our Lagrangian is correct, then expression of Lagrangian is correct. In this case our number of generalized coordinate corresponding to this Lagrangian, number of generalized coordinate is 1, that is simply theta. Our L is in theta, so we have only one generalized coordinate, so definitely we should have only one degree of freedom. So let us evaluate. So degree of freedom is simply 3n minus k. So we have only one particle, a bob of mass m, means we have only one particle, so n is 1. Now we have to find out equation of constant. What is equation of constants for simple pendulum? Equation of constant. So this is in plane, because our pendula is in plane. So we have z equal to 0. There is no motion along z. And we have another equation of constants, which is this one. Because there is a relation between, from this angle we can see that, see, from here we can see that angle is equal to r by L. So S equal to L theta. If this is x, so this is L. So we have this equation of constants. And we have one more equation of constants, which is x square plus y square is equal to L square. So x square plus y square minus L square is equal to 0. So we have two equations of constants. One is z equal to 0 and x square plus y square minus L square is equal to 0. So in this equation we can see that x square plus y square is simply L square, because square of sin square theta plus cos square theta is 1. So we have two equations of constants. So value of k is here, n is 1 and k is 2. So what we have? We have 1. So number of generalized coordinate, which is 1, which is theta, is equal to number of degree of freedom, which is 1. It means it is correct. Means our Lagrangian is correct, and if it is correct, then only we can proceed further. Proceed further means we can only write down the equation of motion. We can only proceed means we can only, if it is correct, then we can only write down the corresponding Lagrangian equation of motion. And once we have a Lagrangian equation of motion, we can easily predict, we can easily find out the instantaneous position, velocity, momentum, acceleration and frequency of our physical system. So this is the way. And one more thing, is that what is this constraint? This constraint is holonomic. This is conservative system, because in this system this is conservative system, and the constraint in this case is holonomic, because we can express in the form of equation which is FRT is equal to 0. So z equal to 0 and x square plus y square minus L square is equal to 0. So we have so many objective questions corresponding to this pendulum. What is equation of constraints? How many equation of constraints? What is the value of k? What is the degree of freedom? What is the generalized coordinate? Means how many number of independent ways our pendula can have motion. So we have only one independent way. So statement question also we can, someone ask the statement question also. If we have this physical system corresponding to this physical system, how many number of independent ways? So we have only one independent way through which our simple pendula, that is in theta, it move only in theta. Though it is in plane, this pendula is in plane, but we have a hidden constraints. That constraint is x square plus y square. Otherwise we have only one constraint that we can visualize, because our pendula is in plane, so there is no z component, z equal to 0, but in this case we have hidden constraints. That constraint is because there is a relation between L and x and theta, so that relation is x square plus y square minus L square is equal to 0. So we have one more additional constraints, and this is the beauty of this mechanics, because if we are able to write the equation of constraints, it means we are simply eliminating the force. We are simply eliminating the component of force which we are bound to write in Newtonian mechanics, but there is no, because we have this, there is no relevant of that constraint force, because constraint force never play a role in equation of motion or in trajectory of motion or any or to study the mechanics of any physical system. So that is why, because of these two constraints, we have only one independent way through which our pendula can move. So कितने questions इसमें पूछे जा सकते हैं? So there are variety of questions. कि what is set up a Lagrangian equation of motion? Set up a Lagrangian equation of motion. Write down the equation of constraints. Write down the degree of freedom. Write down the generalized number of generalized coordinates. So there are so many questions corresponding to this one physical system that can be asked. So our Lagrangian is current. Next we have a Lagrangian. So we can, in earlier case, we can simply set up a Lagrangian equation of motion corresponding to this physical system. So Lagrangian equation of motion. So because we have how many number of Lagrangian of one more additional question that can be asked, if we have a profile of this Lagrangian, then how many number of Lagrangian equation of motion can be written? So we have only one generalized coordinate, so we can only one Lagrangian equation of motion. So d by dt of our qk is theta, del L upon del theta, which is equal to 0. So this is theta. So del L upon del theta dot is d by dt of ml square theta dot minus del L upon del theta is simply mgl cos becomes sine. mgl sine theta. So our del L upon del is simply this is minus, and minus minus becomes plus. So this is mgl sine theta. So ml square theta double dot d theta by dt is theta double dot plus mgl sine theta is equal to 0. So theta double dot plus g by l sine theta is 0. This is Lagrangian equation of motion corresponding to this simple pendulum. In earlier case we have again x double dot plus, let's say this is omega square again. If someone asks whether the simple pendulum is linear system or non-linear, so this is, in one word we can say that physically this is highly non-linear physical system. So simple pendulum is simply highly non-linear physical system, because this differential equation is second order non-linear differential equation, because we have sin theta term. We have sin theta term. Because of that, this is non-linear. So you should know what is linear and what is non-linear, and what is linear differential equation and what is non-linear. So we cannot solve non-linear differential equation analytically, means by hand or by any operator method. We have to go for some numerical techniques in order to analyze the solution of non-linear differential equation. But under certain restrictions, we can convert our this non-linear differential equation into second order linear differential equation. This theta double dot is d2 theta by dt square. So if this oscillation is small, so for a small angle oscillation, sin theta is simply theta. In that case, our differential equation is theta double dot. Let me write here instead of here. So our theta double dot is theta double dot plus omega square theta is equal to 0 for small oscillation. Angle oscillation, this sin theta is simply theta. So this is second order linear differential equation. Second order linear differential equation. Now we can solve this differential equation analytically by operator method, and this is, we have already discussed the second order solution of second order differential equation for a spring mass system in earlier lecture. So again, this is the solution of this differential equation is simply a sin omega t plus delta. So this is what we have. This is the complete equation. Once we know that, and this is the displacement equation or simple pendulum. Main equation or simple pendulum, where omega is, in this case our omega is g by L. So omega square is g by L, which implies that omega is simply under root g by L. And what is our time period? 2 pi by omega, which is 2 pi by under root L by g. So in case of simple pendulum, so these are the mechanical parameters. It means in this case we have considered the simple pendulum. We will write each and everything. So once we have a Lagrangian, then we can predict each and everything about this system, about any physical system, instead of this simple pendulum. So how to write L? L is simply T minus B. T is kinetic energy, B is potential energy, and we will write L, then we will write Lagrangian equation of motion, then we will the solution, which is second order linear differential equation under small angle oscillation condition, and the solution is this one, which tells us the instantaneous position of our pendula. What is the position of pendula at t equal to, what is the displacement of our bow at t equal to 0 and at any later time t. And once we know this angular displacement, we can find out angular velocity, angular acceleration, angular momentum, lot of mechanical parameter. And the time period is 2 pi under root L by g. And this time period, in this expression, what we can conclude? Means our pendula is independent of amplitude of vibration. Our pendula is independent of amplitude, means time period t is independent of amplitude. It only depends upon the L and acceleration due to gravity. So there are n number of information corresponding to this physical system. So किसी भी बड़े physical system की एक complete analysis will tell us the lot of objective information, lot of objective question information. So just think of and go and write corresponding to this simple pendulum कितने तरह से एक्सपेरिमेंट ऑब्जेक्टिव क्वेश्चंस पूछे जा सकते हैं, दैट इज क्या होता है, इसका कॉन्स्टेंट्स क्या होगा, नंबर ऑफ इक्वेशन ऑफ कॉन्स्टेंट्स क्या होगा, डिग्री ऑफ फ्रीडम क्या होगा, लैग्रेंजियन क्या होगा, लैग्रेंजियन इक्वेशन ऑफ मोशन क्या होगा, और इसका डिस्प्लेसमेंट इक्वेशन क्या होगा, व्हाट इज द वेलोसिटी, व्हाट इज द टाइम पीरियड. Means there are n number of mathematical and statement question that can be asked through this physical system. So it's all about this simple pendulum. Thank you.